We have in here this mechanism, and our objective today is going to be to build this mechanism in working model 2D. But not only that, we want to make it work, but we want to find the accelerations of a couple of points, of the point A and of course of the point D. Um, the first thing we got to do is to work out the velocity, the kinematics first. So the velocity of the point B for this rotation about a fixed point C is in the vertical direction upwards for the point B. But you see, here's an interesting situation. Because the bar ABD is a rigid body, it follows that there's no relative displacement between A and B. And so wherever B goes at this instant of time, A has to follow. And so the velocity of A and the velocity of B are the same. If the velocity of 2 points on a rigid body are the same, it follows that the body is in translation, so no angular velocity for the body. There's an angular velocity for BC, but at this position, but not for AD. So in here you have the velocity of the okay. The first of all, we calculate the angular velocity of this is going to be 45 RPM, and we convert it into radians per second. So the velocity of B is 45 times 4, 18.85 upwards. We determine that the angular velocity of dA is 0. And so, and here we move on to the accelerations. So in this case, the acceleration of this point of B is the acceleration of C plus the relative acceleration of B with respect to C. So in this case, the angular velocity is BC. So alpha sub B, and it's constant. So alpha sub BC is 0, and alpha of the point B, the tangential acceleration of B, is also 0. But the normal acceleration exists, and that is omega squared, it's omega cross r in vector form, or in algebraic form, omega squared times r, which is what we have in here. Now, the acceleration under plane motion, the acceleration of, we are going to find the accelerations considering this bar and consider the fact that we know the acceleration of B. So what we're going to do is to, let me see if I find it here. There's two graphs superimposed on this, but let's just work out with one at a time. So the first one is the acceleration of B is like this. The acceleration of A, you only know the direction. But the acceleration of the point A is the acceleration of B plus the acceleration of A with respect to B. So this is the tangential acceleration and the tangential acceleration in here. So if you look at the vector equation, you say the acceleration of A is the acceleration of B, which we knew from the prior analysis, plus the acceleration of A with respect to B. And then you decompose it into the vertical components in there.
Sorry, you said that B has no tangential acceleration, right?
That B has no tangential acceleration, right? Because omega is constant. That's why. So here the acceleration of the point D now is obtained as we know, the acceleration of B plus the acceleration of D with respect to B. So that means the acceleration of B, translation with B, plus rotation about B, the acceleration of D. Yeah, so the acceleration of this, the acceleration of this plus omega cross R, which is this acceleration of D with respect to B. Having done this, I would just maybe reduce it in size and put it the solution away for reference. See, there we go. We're gonna reduce it in size. But I am going to come to working model 2D, and I need the solution of this. So use your creativity here, how you work out with working model 2D. Because, let's see, let's go back to the original picture. This guy in here, yeah, this is what we need. Okay, oh, I am covering the menus. Let's just keep it over here. There you go. You can build this many ways, but I think what we need to do is to establish what logically makes sense to me is to draw one link here. We would represent this one. But we also know we need another bigger link. So what I would do is create one like that. From here. You could actually turn it on them, but you need to make it with the right dimensions to make it fit, and that's what I'm telling you. I was just saying that I would let you do that. What I would do is go like this, and using one of the constraints to rotate it about a point, I could actually build it, see, like this. How is that? Hopefully this is all right. And we need to put this kind of pin joint between these two guys. But also I need a pin joint here. And now I should be able to move it, see? Yeah. And I need the ground to be, I need this thing, if I attach it to the ground, it's not gonna move. So I need to do a slider like this key slide joint. I am gonna pass this like that, see? And now watch this. How come it's not want to obey me? What? I don't know. Something is funny here. Oh, I didn't erase it. Oh, bad boy. I might have not erased the thing. Hmm. Let's see, what are we doing here? We need heat slot jump. I'm sorry, what?
Another slot joints, not the heat, another one, the left side.
This one. Oh, because they are, okay, well, let's see. Okay, let's see. Ah, yeah. See, this is really cool. You could actually test it to see if it's gonna work. Thanks. Do you guys know the correction he just made for me? Why that works? No? Okay. This guy here, this one, is a key slot joint. It's just as if you put a little square piece, and that square piece is gonna be the slot needs to follow that. That way we'll use it like on a suspension system that we want to keep it straight. But not on this one. This one is a hinge. It actually should be flexible. What was happening, the reason it wouldn't let me go fast is I was actually bending the pin, but it's not a pin, it was a square. It's like twisting the little square on the key and this one. That will not work. So everybody here,
We cannot cross something on this. If you press wrong, crash.
no, that might be this computer.
So many issues.
Yours works okay, right? Anything? Anything? No. Change the dimension because it might be a little interference.
It doesn't work. You can run it, but you cannot stop.
But then it has to be another. Okay, this is unique to this one. Let me see if everybody's having the same problem. I am doing this video here. Bad boy. Abandon the okay, we might have to. Okay, so now we see that the mobility is okay. And to make it work, I would just put a motor in here. You know, this motor in here. It's like there. Instead, and this could actually work. See, I can actually make this run, but you can see it's going in the opposite direction that we want. So we double click on this one, and instead of this, I'll just put a minus sign in here and close this and say run, and now it does it the right way. Okay, the program that is very this is very smart program because while the solution we have is in one position, it's going to figure out the acceleration of these points of all the positions as it goes around. So watch this. What I would do is, first of all, I want to know about this point, right? So I'm just gonna say define the vector. Well, first of all, I need to select it. You say define the vector, in this case the acceleration, yeah? And I need this point over here too. So I need to have this is a point element. I'm just gonna put the point D over here. I say, okay, that is the point, and I need the acceleration vector also. So watch this. If I do this, look at the vectors. Isn't that wonderful? The computer has calculated those. And we could and not only the acceleration, but I can put the velocity vectors in here, and we will have the both at the same time. I would like that. And in here it says define the velocity vector. And guess what's gonna happen? I'm gonna move it down here. It's gonna plot both of those. Do you see what happens? You have the green ones are the acceleration vectors. The blue ones are the velocity vectors. So we are really, this is a wonderful engineering tool because now you can calculate the velocity and acceleration of any point at any instant of time as it's running. So now we need to build this with the correct dimensions to solve our problem, but basically this is how you build the mechanism. You don't have to do it in the same order as I did, but you could. Okay, so there's a stop and reset.